This is chapter 4, section 5, called linear approximations, also called tangent line approximations, and you'll see why. So if we have the function the square root of x, right here, this function is square root of x. Now, suppose someone said, hey, what is the square root of 1.5? Now, the average person would have no clue. You'd say, if I had a calculator, I might be able to approximate it, but I don't have a calculator. So how could you approximate it? Well, here's the concept. What if I get the tangent line equation at 1? Now, what you can see, I'll give you some examples. If I want to approximate, let's say here, the square root of 3. Well, the actual value of that would be right here. But I can't find that. I mean, I'm not a human calculator. But what if I found the y value of this red line? I'm going to call that red line L of x for the linear approximation. What if I found the y value right there? Don't you agree it's kind of close to the y value there? It's an approximation. Now, what if I wanted to do for 2? So I want the square root of 2. Well, the actual value would be, I don't know. I'm not a calculator again. But if I found the y value on that line, wouldn't that be pretty close? So here, there's a big error, right? That's a pretty big gap. Here, it's pretty close. It's even a smaller gap. So to approximate 1.5, that's in here, those two little dots would be the actual and the approximation. That's the actual. That y value on the red line is the approximation. Those are pretty darn close to one another. So that's what I'm going to do. I'm going to find the equation of the tangent line. We've been doing that all year long. And I will use that equation, find the y values on that to approximate the values of the tangent line. This is called a linear approximation or tangent line approximation. And one thing to take away, here's the point of tangency. If I pick points around the point of tangency, wow, that red line is really close to the black line. But the farther I get away, look at that, the error just grows and grows. So a linear or tangent line approximation is only good close to the points of tangency. So you want to pick a point of tangency that's close to the point you're trying to approximate. So here is the definition formula in your book. I don't like this because this looks weird. It's like, I'm going to have to memorize another formula, but you're really not memorizing another formula. So you have f of x, and the point of tangency is at A. A is the point of tangency at A. So you want, here's the deal. This is just the formula you've used all year long. Let me change this to slope, and I'll go one by one. You learned from the beginning of the year, I've been emphasizing you have to know the equation of a line. Now, you'd have to know a couple things. You would have to know x1, y1, and you would need the slope. If you had those two things, you can get the equation of any line. Well, what are we looking at? We're looking at a tangent line. Tangent line approximation. We want the equation of a tangent line. Well, here's a question. What is the point? What is x1, y1? x1, y1 is a point of tangency. They tell us it's at A. So x1 is A. What's y1? Well, how do you get the y coordinate of any function? You plug it in, you plug the x coordinate into the function. So the y coordinate is going to be the function evaluated at A. That's your y1. And then, I've asked you this a million times, how do you find the slope of a tangent line? You've told me a million times it is the derivative, and we want it at A, y at A, because that's the point of tangency. We want the slope at that point. So we're going to plug all these things into the equation. y1 is f of A. The slope is the derivative at A, and x is A. Now if we solve for y, we're going to add f of A to both sides, and here's what we get. Y equals the derivative at A times x minus A plus f at A. Look familiar? That is that. And we call this the linear approximation, so we use L of x for our function. So, what am I trying to say? All you do is what you've done all year long. You find the equation of the tangent line, you add the y1 to the other side. That is how you use a linear approximation. So you don't have to learn this new fancy formula. Just find the equation of the tangent line just like before. Get y by itself by adding that to the other side, and you have your linear approximation equation. Okay? So we're just going to do a bunch of examples. We have sine x. We want to approximate the sine of 0.75. So that's sine of 0.75. Now, unless you are some kind of a weird genius, I don't know how to do that other than a calculator. If you don't have your calculator, you're going to have to approximate it. So here's the question. I need a point close to 0.75 where I can get the equation of my tangent line. So what number's close to 0.75 where I do know the sine of? Okay? And here's what we're going to use, that, because that's about 3. 3/4 is about 0.75. So this point is really close to that point. And like we saw earlier, we want a point of tangency that's really close to our point we're approximating to be accurate. Because remember, the farther you get away, so here's our point of tangency here. The farther you get away, the bigger the error. So you want a point that's really close. So therefore, this is really close to 0.75. So let's do this. What's the function at pi over 4? Not the derivative yet. The function at pi over 4, sine of pi over 4, I know that. That's 1 over radical 2. So that's my y1. So my x1, y1 will be pi over 4, 1 over radical 2. Okay? Let's find the slope. The slope is going to be the derivative at pi over 4. Well, what's the derivative of sine? That's easy. That's cosine of pi over 4. And that's also 1 over radical 2. Okay? So we are ready to get the equation of our line. Well, y1 is 1 over radical 2. The slope is 1 over radical 2. The x1 is pi over 4. I'm going to add the 1 over radical 2 to the other side. And we're going to call this our linear approximation formula. So what have we just done? We found the equation of the tangent line at 0.4, or pi over 4. There's pi over 4. This line that we have here, that is L of x. And this is f of x. So where's 0.75? So this is bigger than 0.75, tiny bit bigger. So the actual 0.75, I'm going to exaggerate. It's over here. There's 0.75. So the actual is here. The approximation's there. They're so close. If I zoomed in, I could differentiate it, but they're almost the same. So here's what we're going to say. Sine of 0.75 is approximately equal to, we will take this equation here and replace x with 0.75. So we're going to get 1 over radical 2, 0.75 minus pi over 4 plus 1 over radical 2. This is our approximation for sine of 0.75. You don't need to know the sign. There's no sign involved here. You just need to do those calculations, which is just basic algebra. I wouldn't want to do that, but yeah. And you might say, well, you need the square root of 2, you need a calculator. So you're right, we do need a calculator on that, but there are other ones where we can make values where we don't need a calculator to figure that out. Okay, so that's example 1, linear approximations. Let's go to another example. Okay, we want to approximate the square root of 110. Again, I don't know how to do that. I don't, because I am not a calculator. But here's what I recognize. This is the square root function. And do I know the square root at any point near there? Hey, I know the square root of 100 is 10, right? So that's a smart point to pick. I'm going to pick the point 110 as my point of tangency because that's close to 110, which is somewhere around here. And again, if you look, wow, that red line and the black line are almost on top of each other. If we're out here, wow, that's wildly inaccurate. But look, that's pretty darn close right there. So I need to find stuff. What am I finding? So in other words, f of 100 is 10. So the point there is 100 comma 10. That's our x1, y1. That's our point of tangency. Now the derivative will give us our slope, but you know that's 1 over 2 radical x. Well, I hope you know. So the slope will be the derivative at 100, which is 1 over 2 radical 100, which is 1 over 20. So we do our equation, and I know my y1 is 10. I know my slope is 1/20th, and I know my x1 is 100. So here is my equation for, I'll call my linear approximation. It's 1/20th, x minus 100 plus 10, because all I did is add that 10 to the other side. So this, the square root of 110, is approximated by L of 110, which is 1/20th, 110 minus 100 plus 10, which is 1/20th of 10 plus 10, which is 10.5. That is my approximation. Okay? For fun, in my calculator, I'm going to get the actual value. So that was an approximation. Let's look and see how accurate this is. In my calculator, square root of 110 is, wow, you're going to like this. This is really cool. Is 10.488. Man, that is pretty darn close if you ask me. So that is another example of a linear approximation. Let's see how many more I have to go. Okay, almost done. This is hopefully not too long of a video. Okay, I want to approximate ln of 0.5. Again, I don't know what that is. I have no clue. If I had a calculator, I would. So what ln's do I know? I know ln of 1 is 0. So I know I have a point 1 comma 0, and the tangent line, that's at that point. Now, my error here is going to be pretty large because 0.5 is here, but that's a pretty big jump. You can see that it's not going to be super accurate. Here's the actual value. If I use this line, which I'll call L of x, it's going to be there. There's going to be a pretty decent jump there. So again, if I want to be accurate, I would want to be a closer point, like 0.9 would be better. I don't know why I did negative there. So for 0.5, this is not going to be too accurate, but we're doing an approximation. So we have our x1, y1. That is a point that's really close, well, relatively close to the point we're being approximated. Now, the derivative, my function, you should be able to see, is ln of x. So the derivative is 1 over x. The slope at 1, 0 is going to be the derivative at 1, which is 1. So now we do our equation, y minus y1 equals mx minus x1. So y minus 0, because that's my y1, equals 1 x minus 1, because that's my x1. So we get this equation, y equals x. Wow, seriously? That's it. So my linear approximation formula is going to be x. So my linear approximation, ln at 0.5, is approximate equal to L at 0.5, which is 0.5. Okay, let's see how accurate that is. What is the ln of 0.5 in actuality? Well, it's still going to be approximation because I'm going to round off, but in my calculator, ln of 0.5, okay, negative 0.693. And you could see from this, here's the actual value, there's my approximation. It's a pretty big jump. That's a pretty big jump. Oh, that's, okay, something's not right here. Oh, I see what happened here. I am a lame-o, and that's my name-o. Look here, it's x minus 1, right? So this needs to be changed. It's x 0.5 minus 1. I forgot the minus 1 here. Pretty lame-o. Oh, dude. L at 0.5, which is 0.5 minus 1, which is negative 0.5. Okay, that's better. So that's negative 0.5. The actual value is way lower, negative 0.693. But again, there's a big error here because I'm pretty far from 1, and you can see that there was going to be an error. And just a side note, notice our estimate is above the actual value, bigger. So that's bigger than that. Just a note that we're going to take a look at later. And again, our approximation here, the red line is above the black line, so our estimate is going to be bigger than the actual value. Let's talk about over and under estimates. So when you're doing linear or tangent line approximations, I'm going to make this statement, and you have to know this. This is super important. If the second derivative is positive, so concave up, from the point of tangency to the point being estimated, so concave up, say we're here, and we do our tangent line. I'll actually draw something. No, I should use the actual example, right? These are both concave up. Concave up, concave up. So the second derivative is positive, meaning concave up. And so let's look at a couple things. Here is the point of tangency. Suppose we're approximating the value at, we'll say, right here. So let's look at our 2 points that we have. This is our approximation. This is the actual value, right? Look, that is an underestimate. It's lower than the actual value. So our tangent line is underneath when we have a concave up. So if the second derivative is positive, then our estimate's underneath, or our tangent line's underneath. It's an underestimate. We look at this example here. We have a point of tangency right there. And if it's concave up, it's pretty obvious to see. Suppose we're estimating here. This is the approximation. That's the actual. Now, it's easy to see the tangent line is underneath when it's concave up. So when the second derivative is positive, we have an underestimate. And I have to make the statement, it has to be concave up from this point to the point being estimated. In that region, it's got to be concave up. That's why it says from the point of tangency to the point being approximated. Okay? So from here to here, it needs to be concave up. From here to here, it needs to be concave up. So that's an important caveat, because what if you found here it's concave up, but then it went concave down, and then your approximate, that's like underneath that, and it no longer is valid. So it needs to be, second derivative has to be positive in the whole region we're looking at. And this becomes quite obvious. The second derivative is negative, concave down, concave down. We'll look at our tangent line. Clearly the tangent line is above the graph. So the tangent line is an overestimate. Same thing here. This tangent line, if you have a concave down, the tangent line's above. Definitely going to be an overestimate. So you have to make sure, check the second derivative in the region you're looking at. If the second derivative is negative, you have an overestimate. If the second derivative is negative, you have an underestimate. And hopefully you haven't memorized that. It should be very intuitive on that. We're almost done. We are going to do a linear approximation and determine if it's over or under. And again, it's easy to see here. Oh, clearly under, because it's underneath. But you're not going to always have a picture. So this picture is something I'm doing to help you see what's happening. So what's our function? Our function is 2 to the x. And we want to approximate 2 to the 1.3. I don't have a clue. So how do I approximate it? I'm going to get a line. So what point do I know? 2 to what power do I know? I know 2 to the first power is 2. In other words, f at 1 is 2, or the point 1 comma 2. So if I put a 1 there, I get a 2. So I know 1, 2, and that's where I took my point of tangency there. So I need the slope at that point. I need the derivative. What is the derivative of 2 to the x? I am my own grandpa times the ln of the base. Okay? Well, I want the slope at the point of tangency. That's going to be the derivative at 1. So that's going to be 2 ln 2. And there's my slope. There's my x1. There's my y1. So y minus 2 equals 2 ln 2 x minus 1. So my linear approximation equation will be 2 ln 2 x minus 1 plus 2. I added that to get to the right side. Then 2 to the 1.3 is going to be approximately equal to my linear approximation at 1.3, which is 2 ln 2, 1.3 minus 1 plus 2, which is 2 ln 2 times 0.3 plus 2. I don't know what that line came from. So this is my linear approximation. And the question was asked, is this an over approximation or an under approximation? Good question. So the second derivative tells me over or under. So I'm going to take the second derivative of this function. Now, this is a constant. If I have a constant, let me do it in a different color. A constant, I just copy the constant down. And then I take the derivative of the function, the derivative to the x. I am my own grandpa times the ln of the base. So here is the second derivative. I have ln of 2 twice times 2 to the x. That should be an x, not a 2, folks. Okay, here's my evaluation. You should know what 2 to the x looks like. It's an exponential function. What you realize, this is always positive. And that's always positive. So my conclusion is f double prime is always positive. Therefore, this is an under approximation, is too small. Because the justification, because the second derivative is positive, therefore the linear approximation is an underestimate. And look, it's underneath the graph. So that's what this is all about. Bye-bye.